make sure you're
mic'd.
you're mic'd and that's not on mute.
Yeah, I think I'm mic'd. I mean, he's gonna.
Let's go and get started. We'll run, I guess, here just a minute early, since that never normally happens. So it's really my pleasure to introduce Dina Katabi for our EECS colloquium talk today. Dina doesn't really need any introduction, but I'll still give a brief one, because if I were to go through everything, we only have an hour, and I don't think we'd get through it. But Dina's a professor at MIT, spent her master's and Ph.D. and then decided to stick around at MIT. I had a chance to hear about Dina's work as a grad student my very first year, which I'll tell you about a little bit at the end. But before that, just a little bit about Dina. She's worked in wireless, she's worked in networking, in wireless, in digital health. We're gonna hear about some of her recent work today. She's also incredibly accomplished. Her work has received innumerable awards. In fact, I have to check because there's so many here, but among them, the ACM Computing Prize. She's a member of the National Academy of Engineering and Sciences. She's an ACM Fellow, a Grace Murray Hopper Award winner, a MacArthur Fellow, William R. Bennett, IEEE William R. Bennett Prize winner, an Alfred Sloan Fellowship winner, has a SIGCOMM Test of Time Award, and numerous best papers at SIGCOMM and NSDI. And I think that's an amazing CV, but to me, what's really remarkable about Dina is also her students. If you look at the faculty working in broadly the areas of wireless or applications of wireless at any one of several top universities, you'll see that her students are faculty there. So I think that's a real testament both to Dina's ability to recruit terrific students and advise them all the way through into successful faculty careers. Now, just on a personal note, I first heard of Dina when I was taking a class here as a grad student myself. It was 268, and I remember the faculty members, who are actually both still here, going on and on about how amazing this piece of work called XCP was. And it was a way of basically, as they described it, now keep in mind, this is my 20-year-old memory, and saying it's easy to come up with something that's fair. It's easy to, this is for congestion control on the internet, easy to come up with something that's fair. It's easy to come up with something that does a good job. It's hard to come up with something that does those things and is also friendly to TCP. And this piece of work is this amazing piece of work that does this. And for that, I think Dina has gotten a number of awards, recognitions. So that was my first time I heard about Dina's work. And then I followed her work through a number of other things and many of her students. And so her work and her group have always been an inspiration to me. So it really, really gives me great pleasure to be able to introduce Dina Katabi today. Thank you, Dina.
Thanks, Papa. Sorry, I move a lot. So, hi everyone. It's such a pleasure to be here today. The last time I've been here in Berkeley, maybe over 15 years ago. So it's such a pleasure to be back and see the friendly faces and get to see the people again. So it's amazing. Thank you very much for inviting me to do this. And as Papa was saying, I want to tell you about the area that I've been working in the last 10 years. So I started in networking, computer networks, moved to wireless networks and then sensing. But recently, over the last 5 years, I became very occupied with, can we do something to improve healthcare, to do something to that has application in health? And as you can see from the title of the talk, Beyond Wearables, the Rise of Invisible Health Tech. So let me ask you guys, who has wearables? Who's wearing wearables among you? Lovely. So multiple people are wearing wearables. So that's great. But who are the community that you belong into? So this is community of high-tech people. Much of you are on the younger side. Most of you guys are people who care, like the people who wear wearables are people who care about their health, and they want to be healthier. But this is not the problem of our $5 trillion healthcare system. The problem is typically the people who actually think that they are fine, but then things happen. The problem are people like my grandfather here. So I started working on healthcare scenarios because he lives in Belgium. The whole family lives in other countries, actually. And he had a health, this was like 10, I think 12 years ago. And basically he fell. He ended up in the hospital. And after he was discharged back to the home, we were just all worrying, how is he going to live alone? What do we know about his health? I will call him on the phone when he doesn't answer and just freak out. Should I call my uncle to drive from Paris to go to Brussels to be able to check on him? So the healthcare problem is really about the old and the sick. And it doesn't matter, my grandfather passed away a few years ago, but now I have the same problem with my parents, and forget about trying to convince my parents, at least, about wearing wearables or using them. They just think that they are fine until the problem happens. And in fact, there was even a study that looks at 9,000 individuals and asked them, why did they stop using their wearables? And these are younger people who actually had wearables. And one of the very common answers was, they actually got sick. So when you don't feel well, when you are not like you can hardly move, the last thing on your mind is, I'm going to take my wearable and put it on me because that data is important. So how can we monitor everything that we do with wearables and even more, but from thin air, without asking people to wear wearables? That is a problem that I worked on. And imagine if we can just, from the wireless signal that bounce around, be able to get your breathing, your heartbeat, your sleep, and not just whether you are asleep or awake, but light sleep, deep sleep, REM. Be able even to get your EEG, your brainwave signal, without asking questions, without having to wear any particular sensors. So this is exactly what we do. We developed this device that we call it the Emerald device. And basically, we are able to do this because we leverage a lot what AI can give us, like analyzing the signal using advanced machine learning models. So I'm going to take you through this journey, showing you some of the stuff that we have developed gradually from when we started until now. So this is one of our very early experiments. So here you see my graduate student. This is one of our offices at MIT. Actually, this guy now is professor. So it worked well for him, this research. And we are going to monitor him through the wall from the adjacent office because wireless signal traverse walls. And here what you see, this dot, is where the device thinks that he's standing right now. So let me play this for you. And you can see as he moves, the red dot is moving with him.
The red dot is the device?
No, the red dot is where the device thinks that he's standing right now. The device is not even in the same office. Yeah, it's like imagine somebody is monitoring us from behind this wall. And as you can see, it tracks him pretty well. He doesn't have wearables on himself, nothing. It's just because when he moves, he changes the electromagnetic waves around him because our body is made of water, so any movement changes that electromagnetic waves. Now, this is actually what we used to be able to do a while ago. So this is from 2017. But let me show you what we can do today. So now this big frame is what the wireless device can see through the wall. And this is what's happening inside the room so that you can tell what's going on. So now what we can get the full skeleton without camera through a wall with the wireless signal. So you can see now he's not just a dot on the floor map. He sits, you see him sitting. He stands up, you see him standing. He moves his right foot, you see the right foot, the left foot, all with just wireless signal basically X-ray vision through walls. Now, everything that we do, of course, we compare to the gold standard, showing that it is quite accurate. And in the case of actually movement, is something called the Viken motion capture room. So it's a room that planted where the ceiling is planted with infrared cameras, and you put infrared markers on the person to show that the motion is quite accurate. But can we get things that have nothing to do with, like, in principle, motion? Actually, even before that, so let me show you. This is, we get the action. So here, like, so that thing is with the RF signal, and now you can see, like, he's gonna imitate, like, combing his hair. You see that the wireless signal knows that he's combing his hair. So he's, like, imitating, like, picking a cob. So basically, we can put these devices in the home, and we can know, like, what the people are doing without putting cameras, without seeing too much details that people don't want to reveal. We also can get your sleep. So when you go to sleep, your brain waves change, and you enter different stages: awake, light sleep, deep sleep, and rapid eye movements. So these sleep stages, I mean, of course, they are important for sleep disorders, and we know that in the US, 1 in every 3 people has some sleep problem. But actually, it's more important than that, because sleep is a platform for almost all diseases, particularly any neurological diseases, but in general, everything interacts with sleep. So today, if you want really very accurate sleep staging, you send someone to a sleep lab, they put these electrodes on his head and body, and they ask him to sleep like this. This is how you get accurate sleep staging. Now, your Apple Watch can give you some information. It's not actually as accurate as our system that doesn't touch you. So let me show you. So this is our device, transmits very low power wireless signal, analyzes the reflection using AI, and spits out something called the sleep hypnogram. So what a sleep hypnogram is exactly what you get from Sleep Lab. It tells you for every 30 seconds, like whether your brain is in deep sleep, light sleep, REM, and how it is moving between these stages, as you can see. And this is actually, we did so many studies, but we actually compared to the gold standard, which is what's called PSG, with all of these electrodes and sensors on the person's head and body, and we show that we are very accurate. In fact, the accuracy is comparable to 2 sleep technicians looking at the same data and having this agreement between them, because, like, one can say, oh, this is light sleep, this is deep sleep. So that is the difference from the ground truth. This person is sitting like you. What you see is he inhales and exhales. We asked him to stop breathing, hold his breath. So you see the signal stays at a steady level because he exhaled and he did not inhale. Again, everything that we do, we compare to the gold standard. So in the case of breathing is FDA-approved breathing belt from Philips. In case of sleep, for example, as I said, is the MGH Sleep Lab, and with all of the data in it. So basically, we have all of this ability to get this data. Now, this is our most recent edition, brain EEG. Now, we cannot get your EEG when you are solving a problem or what you are thinking about. So this many people are like, oh, can you, like, now read my thoughts? No. This is your EEG during sleep. But this is a very detailed EEG. So here, what you see is basically, this is someone who has Alzheimer's disease, and he's 83. And here's this, like, the measured EEG with electrode on his head. And this is the EEG that we generated with our Gen AI model. And this is, of course, one example. Like, we have, like, tried this on over 20,000 different individuals, and the mean absolute error is less than 7%. So we have this, like, ability now to extract a variety of physiological signals from your breathing to your movement to your brain EEG, all without touching the individual. People can live their life, and we collect this signal. So let me tell you, I want to tell you a bit how we, like, actually, even before that, let me show you some other thing that we can do. So here, what you see is, like, the ability to detect diseases and drug response. So this is Parkinson. This is like AUC, like you can interpret it as accuracy. So being able to detect Parkinson's, Alzheimer's, antidepressant drugs. And I'm gonna come back to this as I come back to showing you some of the data from our patient, the patient that we monitor in actual clinical trials. But let me show you a bit about how we do it. And again, I'm going to describe it at a very, very high level, and also gradually how our thinking about it gradually moved and changed. So at a very high level, really there are two components. One component is the radio. So the radio is the ear of the system. If you can't hear the wireless signal, if you can't capture the wireless signal, we can't do much. So we have a lot of understanding, as Prabal was saying. I started from wireless networking and understanding wireless signals and propagation and radios. But really, the thing that opened up and unlocked opportunities is the machine learning, is being able to interpret electromagnetic waves using these new models and learn from data. So as I said, so when we started with thinking the standard way you start as a wireless system, as a wireless researcher, is the closest thing is radar signal. So if you transmit wireless signal, it can, of course, traverse walls and occlusion. It reflects of the human body, and some minute signals come back to your device. So I'm going to explain, I'm going to use motion as the example, and the very simple radar equation is that distance is equal to time multiplied by the speed of light, because electromagnetic waves travel at the speed of light. So we all know the speed of light. So if you want to get movement, one simple thing, which is what is widely used in systems, is you can just measure the reflection time, and then you get the distance of how the person is distant from your antenna. Unfortunately, things are not that simple when you are working in indoor environment and people. So if you try to use just these radar style equations, one of the problems is not only our body reflects the wireless signal, actually everything reflects wireless signal. So if I just transmit wireless signal, the walls are going to reflect it, the chairs are going, the floor is going to reflect it, your body is going to reflect it. So I don't get, it's not like radar, you are lucky if there is one airplane in the sky, it's an empty sky. Here there is a mess of reflector. So the first thing is that you have what we call the signal to noise is very, very low. It's just how do you extract the signal of interest from that noise. The second thing, I'm not just interested in one thing, of course, is a dot on a floor map, but I want to do way more things. I want to extract health metrics, like whether you are in REM sleep or light sleep, and what's your EEG, things that, in principle, is not about motion and distance. So to do that, we started thinking about how we can run AI models that operate on radio signals, as opposed to operating on images or text. Now, nicely, radio signals, maybe the closest is images, like computer vision. But there are so many differences from actually working with radio signals. And so I'm going to, as we started doing this, so it's okay, at the beginning, okay, radar is not going to work for us. Can we actually leverage these models to try to understand the wireless signal? So the first thing that we run into is something called specularity. So let me explain this. So now we are going to have multiple antennas and antenna array to allow us to zoom in on the different part of space. So let's say that you transmit a wireless signal. So when the wireless signal actually hits a reflector, it's not like vision, like you get to see the whole scene. In fact, what happens is some of that wireless signal comes back toward you, but much of it actually deflects from your antennas. So you don't get to see it. So you are only seeing some small spot of the environment, and you are expected to get full information about the person and how they are moving and all of that stuff. So if you put it here with a person, so it means that maybe like in this frame of RF, I get to see like the signal from his hand, but not from his head or chest or from his feet. And then as he moves, maybe now I see his chest, but I don't see like his belly or his head. So like what I see is kind of also messy. Like it's a variety of things that don't represent the same thing. So to deal with specularity, we had to design our neural networks to work across time, okay? So to think about the world is not like images, but in terms of radio, like video clips of radio signal, okay? So if we can collect all of that stuff and work across time, then maybe at different points we see like the hand and the leg and sometimes the head. And like think about like if you are in like in a club, for example, and they have spotty lights, and sometimes it shows this head, sometimes it shows this part, and you have to like put everything together so that you can extract really what happened in the environment. Now, the problem with that is that this signal is huge. And so just to put it in context, so today, so this was in 2018. Today, even like as we work with video, with like generative AI, like Sora, for example, can generate like, we talk about like few seconds to minutes, like because actually working with large context is very problematic. It's like difficult managing the context. So RF actually is not three-dimensional like video, it's actually four-dimensional. Now, in addition to the fact that it is complex numbers, not just like real numbers, but it's four-dimensional because there is also depth. So you have like 3 dimensions of space in addition to time. So it's huge. So we needed to do something to be able to run the neural networks on this. So here I think it's very, very important when you are taking machine learning, the domain knowledge was essential. It was essential that we know a lot about radio signals and propagation systems so that we were able to come up with a solution that decomposes a 4-dimensional radio signal into 2 3-dimensional video clips. And we were even able to formally prove that operating our model on these 2 3-dimensional systems is equivalent to operating on the 4-dimensional data.
Can you tell us what the 4 dimensions are?
Sure. So 3 dimensions of space and 1 dimension of time. Yeah. And that got us 200 speed up so that we can do this. So, okay, now we can run these neural network on the data. But what is next? How do you get actually supervision when your signal is RF? Right? So how do you label radio signals? So again, like when you think about machine learning at like with images and like ImageNet and like what we had, like that started all of the advancement in computer vision, you had like a large data set of labeled images. We don't have the equivalent in RF. So how do we label RF? So if you label images, I mean, basically you give them to a person, and let's say that you want to get the skeleton. So what they do is that they label what's called key points, like the knees, the elbows, the shoulders, etc., so that you get labeled data. But if you give radio signal to a person and say, please label for me where the shoulder is and where the head is, it's not going to work. So how do you do it? So the only way to do it is to think about a surrogate system. And interestingly, the surrogate system comes from computer vision. So basically what we did, so again, remember, radio signals actually are like they give you depth, which is an image doesn't give you. So we had to take like multiple camera systems and create multiple views so that we don't miss the depth that comes with radio signal, combine the view with multi-view geometry to create the actual geometry of the environment, and then here label the individual frames from the camera using machine learning model that were trained on images, and now we have labeled data. But this is a huge system. Imagine having to put plant actual just to train your system. You have to put 12 cameras all around and combine these views, and with just with very detailed calibration to be able to do this. But once you do it, you are combining now. You have a system of cameras, and you have your radio signal. This system, we know how to train using computer vision. Now, this system, after it is trained, can teach this student. So you can think about teacher-student. So computer vision is the teacher, and the radio neural network is the student. And now you get the label from the computer vision. But after you trained, you don't care about the computer vision anymore. You can take this and just work only during inference with only radio signal.
How do you synchronize images and radio signals?
It's a disaster, basically. So you have to run, we use the same, basically we use NTP, but we connect everything to the same NTP server. And we have to be very careful about calibration, and also use a very special motion to recalibrate with those motion. But yeah, you are running a humongous system that is has so many cameras and radios and all of that stuff just to do training. So the next thing that we were thinking about, okay, so this is difficult. We can't do this to collect a huge amount of data. So can we use self-supervision? So luckily at the time, there is a lot of work that started in computer vision about self-supervision using contrastive learning and mask autoencoder. And I'm not going to get into the whole details. It's actually not, there are so many things that you need to do to transfer this to the wireless domain. But basically, we started using self-supervision. But instead of using something like mask autoencoder on images, so basically the self-supervision is can we recreate the missing RF signal? So can we actually teach a model to recreate the RF signal? And to be able to do this, the model has to understand a lot about RF signal. So that reduces the amount of data that you need. And you can then use, with a bit of supervised data, you can go very long way. So we were very excited. The system started working really terrifically. Can even differentiate different people. We had differentiated 100 people in the lab. And then we started using this in the homes, and nothing worked. So you take something and you go to the home and you discover, wow, how do I generalize to new environments? So it turns out that wireless signal is very much environment dependent. So we trained in the lab. It works very, very nicely in the lab. And now it goes to a new environment, and the wireless signal reflects off everything, not just the people. And now you have you train, say, for example, in these environment, and it has information that is related to the space and to the environment and the size of the different bodies and all of that stuff. And you want to go to a new environment, it just doesn't work. So you have to do new things to be able to generalize. Basically, we have to understand that there is a lot of the information here that is irrelevant to our task, that is extraneous, like the information about the environment. We are not here, our goal is not to discover that there is a bed here and what is the size of the bed, and that there is, we want to track people and their physiological signals. So the people and the physiological signals of the people is the relevant information, and everything else is extraneous information. So can we remove the extraneous information? So basically, this is related to a problem that's called multi-source domain adaptation. So basically, you have source domain where you train, and you have target domain where you want to take that trained model and you want it to actually work without a new training. And basically what you want is that if you have these, I hope that you can see a bit that there is like, so this is a domain here, this is domain. So really these like boundary decisions are different between the training and the testing. And what you want is to align all the domains so that the boundary decisions in the training are similar to the boundary decisions in the testing. And one like simple and like was very interesting and new way to do it at the time is adversarial domain adaptation. So how does that work? So you have a signal or like data input, like radio signal in our case, and like could be images, for example. You are encoding it to some representation, and then you are decoding that representation to something of interest. Could be like, in our case, some health-related metric. And this representation, what you want to do is you want to remove the extraneous information from it and leave the good information. So how do you remove the extraneous information about the domain? In our case, a domain is a home, is like a training environment. How do we do that? So there's something called a discriminator. So I'm going to take this representation, and I'm going to train here a neural network, and I'm going to train that neural network to discover where this representation, where the signal is coming from, which home. Now, if this discriminator at some point is unable, like I'm going to actually train the network to fool the discriminator, not to help it, to fool the discriminator. And if the discriminator cannot tell which domain the data comes from, then that extraneous information about the home has disappeared from this representation, E of X. So this is like you're trying to fool the discriminator, so your loss is like positive for the predictor, but negative for the discriminator. Now, guess what happens is that actually you remove also the useful information. Because, I mean, also like some of the information that allows the discriminator to say this is Alice's home is how Alice looks and her height and some of that information. So how do you like keep the useful information but remove the information that is extraneous? So we came up with something called conditional discriminator. So basically, it's at a very high level is the idea is give the discriminator the information that you think is useful, that you don't want to remove, which is effectively the prediction. So if you give the discrimination, if you condition the discriminator on the prediction, now the training doesn't win anything by fooling the discriminator to like eliminate the information about the prediction because it is there anyway. It is part of the input of the discriminator. So what we were able to prove is that this conditional discriminator at equilibrium is going to remove the extraneous information and keep only the useful information that we are interested in.
And you define the useful information?
As useful information that are related to the health metrics. So we like, for example, it could be like the sleep hypnogram, the sleep staging. It could be the location of like a key point on the body. Whatever information that you want to keep, that's the one that you are training your predictor to predict. There was a question up there?
Yeah, so two questions. So first is, what is the frequency you are using in development?
Yeah.
And the second question is, so for a given physiological detail of interest, so how do you know in advance if it is measurable? Because before running the machinery of AI, etc., so if I am interested in a particular physiological detail, so can you say in advance if it will be measurable?
Okay. So what is the frequency? So the frequency that we use in our system, we use what is called ultra-wideband system. And the frequency were between, I remember, like I think 5.8 to like 7.2, something like that. But basically, it is like centered around something that is similar to Wi-Fi, but it is lower power and wider band. Okay? And the reason why you want to do this is you want something that is basically, it has a lot of information about the environment from this ultra-wideband thing because the bandwidth is wide, but also it does not interfere with Wi-Fi, does not interfere with cellular. Also, cellular and Wi-Fi don't interfere with it. And also, it traverses walls and occlusions. Now, how do you know that there is actually a health metric, the health metric of interest in the data? I would say you don't know for sure. Like, when we started, I knew that we can get the dot on the floor map. That's like we all knew in my community at the time. But that you can get the full skeleton from the wireless signal with like that you can like tell what the person is doing through a wall. I mean, if you asked me at the time, I was no, unlikely, particularly at these frequencies. Maybe you have to go to millimeter wave to get the resolution that is needed. But it turned out that we can. And if you ask me, we could get someone sleep staging, which is not really about motion, I would say no, but then it turns out that it's possible. And again, like this last thing about EEG, it took us much longer time to figure out how to do it. And so when we reach here, like, we were really happy. We have the system that can get you motion, can get you sleep, can get you respiration, even the pulsing actually of the blood, it can get you. But EEG actually is much like more complex signal. So we didn't know that we can get this. But then something interesting happened. Gen AI arrived. And we started thinking like, maybe what we are doing actually is generative. In a sense, like what we are doing is that we are taking a prompt from the wireless signal, and we are generating some different modality that is related to a health metric. So if you think about Gen AI, so today, like Gen AI, you see something like this. So you take a prompt that is text, and you can generate, for example, a different modality, like a picture. So like, for example, here, a corgi playing flame, and it will generate that, like it's playing trumpet, and it generates the trumpet and the corgi. And then the important thing about the Gen AI is that what it generates has to be consistent with its prompt. So what if we can do this? What if we can take the wireless signal that bounces off someone's body and somehow say this is a prompt to the system? Like, I want you to generate a health metric, say like their EEG, but I want this EEG to be consistent with this wireless signal being reflected of this person's body at this particular time. Otherwise, this is not a good answer for this particular prompt. Now, of course, like whether this is possible or not, we don't know, but it seems like reasonable as a starting point. And the other thing is that if you think about it, actually, there is a lot of similarity between text and physiological signals. So here's like when we look at text and when you look at Gen AI in text, what happens is that you are leveraging the fact that text is a sequence of words from a dictionary, a finite dictionary, okay? And that those words come after each other according to certain rules. And this is how we learn with Gen AI. Predicts the next word, predicts the next word, correct? So now if you think about physiological signal, let's take again our signal of interest here, like the EEG of the person, but any physiological signal, really it's a sequence of patterns. These are not random patterns. There is a finite set of patterns that our brain generates. Right? It's just like we don't know that dictionary. There is a dictionary of EEG patterns, but we don't know it a priori. It's not like the English dictionary. We know it a priori. And also there are rules. Like, it's not like this pattern comes after this pattern in just a random way. There are rules that control like which pattern can come after which pattern. So in principle, LLM should be applicable in some sort. And this is exactly what we did. So this is our most recent types of models. So they are LLM inspired. They go through two stages. The first stage is something called in deep learning tokenization, which is basically, I don't know the dictionary of EEG patterns, but I know it's a dictionary of tokens, of patterns, so let me learn it. Let me learn that dictionary. Once I learn the dictionary, now I can use a generative model that, conditioned on a prompt, I can generate from that dictionary. And that is much easier than generating from a word that is infinite that has not been learned. Okay? And actually, it turned out that it actually works. And I showed you that it can generate the EEG of people correctly. So these are like, of course, very, very high-level description of how these models work. But this allowed us to create all of this collection of signals, of health-related signals, from effectively thin air. Gianni?
I'm curious, I mean, EEG data is medical data, and I imagine there's some privacy law. It's like subject to privacy laws. Do you end up using differential privacy or something like
No,
this?
I use the exact same privacy that is used in clinical trials. So basically, that's one of the things. So we actually have been, for the last 4 years, we have been working with pharma and like medical doctors and healthcare systems. And these devices that we are talking, this technology as we are talking now, it is deployed in the homes of individuals with Parkinson's, with ALS, with Alzheimer's, Crohn's, lupus. And we deal with it the same way as you deal with privacy in medical systems. Basically, you have to, anything that you do, you have to go through an IRB, like an ethic board that would say this is ethical, and you have to do to do something called informed consent. So you can't monitor anyone without telling them exactly what you are monitoring, what you are extracting, and have them sign that it's okay with them. And there are other things that we have developed, like that would prevent somebody, for example, to monitor a person against their own will. But one very important thing is just we follow privacy rules the same way as like when somebody is developing new drugs. Let me just go through a few slides and we'll come back. So I want to show you a few results from actual like clinical trials with real patients. Now, some of the trials that have new drugs we cannot show you for NDA reason, but I can show you some of the ones that are like under like that we did from that don't have new drugs. So it's like called natural history. So Parkinson's. Parkinson's is the fastest growing neurological disease and the second most common neurological disease after Alzheimer's. And one of the problems with Parkinson's, like Alzheimer's, like many of these neurodegenerative diseases, is actually the disease starts in the brain 10 years before like the person starts developing the motor symptoms, the tremor and the stiffness of motion. The problem is that we detect the disease when the motor symptoms happen, because this is what we can see. We can say, oh, now it seems that this person has Parkinson. But by the time these motor symptoms happen, the dopaminergic neurons in the brain, they are 50 to 80% already impaired. So imagine a disease that you detect at a time when 80% of the neurons are already dead. I mean, how much chance we have at curing that disease? So if we want to do anything, we really need to try to detect Parkinson without the motor symptoms from what is called autonomic symptoms, like that are autonomic system, like your respiration or sleep. These are autonomic things that happen before the motor symptom. So what we said, okay, can our AI detect Parkinson's from breathing, from nocturnal breathing, without any motor symptoms? People, even if they have Parkinson, even if they tremor, when they sleep, surprisingly, there is no tremor. So again, like much of what we do, we have a guess, but we really don't know whether it's going to work or not. Like when I ask the doctor that I work with, the Parkinson expert, like, can you actually diagnose Parkinson from someone's breathing? He said, good luck. No. But it turns out that you can. So we check these respiratory signals. It's very easy for us. I told you that we can get it from thin air. We train a neural network to answer two questions. Does this person have Parkinson's? And if they do, what is the severity of their disease according to the gold standard? And this is actually, it's a very large study. We have like more than 7,000 individuals. 700 of them have Parkinson. It involved Mayo Clinic, MGH, and University of Rochester. And let me show you the results. So these graphs are very common both in medicine and in machine learning. On one axis, you have specificity. On the other axis, you have sensitivity. And what is important is the AUC. And typically you interpret the AUC at the accuracy. So we can, from wireless signal that bounce off someone's body during their sleep and getting their breathing from that wireless signal, I can tell you that that person has, from one night of sleep, Parkinson or not, with an AUC of 90%.
This is before the tremors?
Sorry, what?
This is before the tremors have started or after?
So give me a break. Like, I'm going to come back to this, okay? And in fact, I can tell you it's like from breathing, whether you got from wireless or you got it from a breathing belt, like FDA-approved breathing belt, because just like, it doesn't matter. The wireless breathing is very much similar to the breathing that you get from a breathing belt. Now the interesting question, can you do it before actually the doctor diagnoses the disease? And this is a much harder question because there is very little data that we have about people who eventually develop Parkinson's disease. But it turned out that there is one data set that has respiratory signal from 2 visits to the clinic that are separated by 6 years. And there are people who came in the first visit and they said, I don't have Parkinson. But 6 years later when they came, they said, I got diagnosed with Parkinson's. So the blue guys are the guys who 6 years later, they came and they said, I was diagnosed with Parkinson's sometime in those 6 years. We don't know when. And the red ones are the ones who never developed Parkinson during those 6 years. And you can see that the model already knows that there is something different about those guys who eventually develop Parkinson's. At least 75% is saying, 75% of them, I actually think that they do have Parkinson's already. So to answer your question, this is, of course, in medicine, we really want like much larger data set to be able to make sure that this works across different scenarios, different ages. Like also Parkinson is a very complex disease, like how much earlier we know. But it seems that it can actually get some early signal pre-diagnosis.
So this was pre-diagnosed by 6 years.
I mean, we don't know when exactly it got diagnosed, but we heard the data comes from them 6 years later after the experiment that we ran on. I want to end with another neurological condition very quickly, which is depression. So mental health is a big problem. And one of the things about mental health is that we don't have tools. It's not like you can do a blood test or even, like, there are very, very few tools to, like, be able to really have tests of mental health. Like, somebody has depression, they go to the doctor, they give them antidepressant, they ask them, how do you feel? Right? And we hear a lot about placebo and all of that stuff. And one of the things that is really important to realize is that when people don't take their antidepressant, actually there is a huge risk of suicide. In fact, in the US, like I was, before coming to here, in Boston, I was in like a summit about psychiatry, and they were saying that 50,000 people in the US die because of suicide that is related to depression, and that's not about opioid overdose, it's just the depression effect. And this is actually more than the people who die because of breast cancer per year. So being able to detect that somebody is using their antidepressant, they didn't stop, like that they are adherent to the antidepressant is very, very important, particularly when they are suicide risk. So it turns out that actually antidepressant changes sleep, and if we use AI, we can actually detect that change very effectively. So I just going to like show you like how a sleep hypnogram looks like. So this is like somebody who went to sleep around midnight, slightly before midnight, and this is the sleep onset, then they move to light sleep, then deep sleep, and then REM. We know that sleep goes in cycles. Every cycle actually ends either in REM or awakening. So this is 4 cycles. Now, if you have someone who's not taking antidepressant, so what we did here is that the x-axis is time since sleep onset. The y-axis is many, many nights, because actually once you put the wireless device, you can, like this is like 6 months of data stacked night after night after night. Everything that's colored is REM. Everything that is black is non-REM. Could be like light sleep, deep sleep, etc. So when somebody is not taking antidepressant, look at this wonderful, like very well-structured REM architecture. When someone is on antidepressant, it's obvious what's happening. You get suppression of the first REM cycle. Not every night, but with high probability. So this is why traditionally, when people don't have this kind of data, like stacking like 6 months of data, so what they tell you is that REM get delayed, as opposed to actually the first cycle of REM actually get suppressed. Now, of course, I don't want to wait 6 months to detect that the person is not taking their antidepressant. I want to be able to detect it from a single night. So what we did is to, again, like, say, OK, so let's use breathing. We know that we can actually, through, like, we can have, like, breathing, like, use, like, move to EEG from breathing. And from that, we're going to ask the question, is this person, like, taking antidepressant or not? And let me show you the results. So this is, again, similar to the previous graph. Specificity, sensitivity, AUC is 85%. So from a single night of data, we are detecting how antidepressant is changing the physiology of that person, no question asked. And it works across different drugs. In fact, it is even easier for the common drugs such as SSRI and SNRI. So these are very common drugs, and we have much higher AUC on them than the less common ones. And this is a person who was put on antidepressant, and you can see the model like jumped and started saying, yeah, actually, I think he is taking antidepressant. And this is a person who was on antidepressant, and the antidepressant started being tapered off to take him in preparation to take him off the antidepressant. And you can see how the model is responding. I want to go back to like the model and talk about foundation model for human physiology. Of course, like one thing is to be able, like similar to text or computer vision, text effectively, like being like, instead of like every task to train a model, like we want to have one foundation model that is operating on human physiology, but that generate a representation that we can use for so many diseases, like not like one model for Alzheimer, one model for Parkinson, one model for antidepressant, one representation that we can tune easily for different tasks. So this is what I mean by foundation model for human physiology. Now, in text, how do you create foundation models? What is the task that we train with? We predict the next word. So we have these autoregressive systems that, GPT is trained that way, mainly. Basically, what is the next word, what is the next word, what is the next word? So that's interesting, but it's not as powerful in the case of physiological signals as it is for text. Because a very important reason that in text, knowing the past is very much predictive of the next word. That's the context of the conversation. If you heard everything that was said, there is not much else to what is the next word that's going to come. In physiological signal, it's not the same thing. Like, even if I give you all the pattern of your EEG, predicting the next pattern depends on two things, the history and the environment. Like, if I touch you, the pattern is going to be different. If there is noise in the environment and you hear it, the pattern is going to be different. So simply predicting the next thing is not enough as a foundational learning task. So what we use effectively is translation. So we discovered that, in fact, if you ask a model to translate one physiological signal to another, it can give you very, very powerful representation of the latent variable that control human physiology. And we use that to generate with one model biomarker for certain drugs and diseases. So for the future, how do I imagine the future? I imagine the future we're going to have invisible health monitoring in at least every patient home. In fact, every home. Why just every patient home? And we're going to have foundation models that interpret and analyze the data. And on top of that, we're going to have AI agents that can communicate to people about their diseases, about their health, and also communicate to the doctor so that we can personalize the health and improve the outcomes. Thank you very much.
Well, thanks very much for a very, very interesting talk, Dina. So I think we have time for maybe a few questions.
So this is terrific. There's a scientist in Israel who's doing something rather similar, but with light waves rather than radio waves. So in radio, we have fading and multipath. The same thing in light waves is called speckle. And what he does is he illuminates, say, a person, doesn't even know he's being illuminated with laser speckle, and can monitor very small motions and can learn a huge amount from that type of information. I don't think he started on the AI part, though. So there's a lot yet to be done.
Yeah.
But what do you think about switching from radio waves to light waves?
So, I mean, I don't know about that specific work, and I mean, I think from your description it's quite interesting. But I think one of the things that is important for me is to be able to track health with zero, engagement from the individual. Like, we can live our life and our health can be tracked to the level that we can understand the development of diseases and get the signal early on and move from sick care to health care, really. So like when you're talking about light, I would assume that the person has to be engaged. So you have to focus the light.
No, you could pass people on the street; they wouldn't even know that.
I see. So that would be interesting. Then, okay. So then maybe we can combine that also with the AI to give it much stronger.
I think so.
Yeah.
Yeah, thank you so much for coming here and talking today. That was really engaging. I have a quick question on whether you could see the potential of the signals being applied more towards physical injuries, especially since there's a huge amount of the US population and abroad who have a lot of chronic injuries, especially in elderly people. They're more likely to have falls in the home or even outside of home, and whether this radio signal can, I guess, be able to track the injury from a musculoskeletal level.
So, I mean, of course, so the answer is yes. I mean, of course, there are different scenarios, but for example, with injuries, I mean, one of the things is that I showed you that we get the skeleton, the whole posture. So, for example, injury typically is if you have your hand injured, for example, it becomes the movement span becomes less, for example. If you start doing PT, for example, it improves your movement and the movement becomes more normal. So you could do a variety of these things.
So you can potentially do gait assessments.
Yeah.
As well.
Yeah, in fact, we have work on gait in Parkinson disease. I skipped today, but happy to show you.
Thank you for the very nice talk. I'm curious about the EEG example. So EEG is extremely weak signal at low frequencies. Is there any physical possibility that you're actually picking this up on the Wi-Fi on the receiver, or do you think that the model is purely inferring this from other physiological signs?
Yeah. So I think sometimes people think that we are capturing the actual electric wave that is from the brain. In fact, no, that's not what is happening here, because I mean that signal is even when you put the electrode, it's very weak, and the hair even, it just makes it weaker. So what's happening here is basically there is a huge crosstalk in the body that we don't understand, and current medicine does not understand the level of crosstalk. That what we showed, the pure fact that I can predict your EEG from your respiratory signal, it means that there are latent variables that capture a lot of information about your health, at least the chronic conditions. I'm not talking about, what you are thinking now or something like this, but there are latent variables registries, if you like, in the language of computer science. So we have registry, memory, stuff like this inside our bodies that they are hidden, they are latent variables, but they express themselves through our physiological signals. And I mean, the translation is not perfect, of course, but what this model is doing is the inverse transform. It's trying to like go from the observable through the latent variables to another observable type of signals.
Got time for maybe one or two more questions.
Hi, that was an awesome talk. To kind of follow up on that question, what would you say is kind of the limit of resolution with this method? A lot of what you showed is like behavioral level, but for more granular stuff like seizure detection or something like that, what would you say is like the limit of how much resolution you can get?
So it's really hard to tell the limit because, as I said, like even if you ask me, like now I can show you that we can get an accurate representation of one's EEG. Now again, this is like a single channel EEG, it's not multi-channel EEG. What is the exact, like can we improve the resolution beyond this? Can we get multi-channel EEG? I really don't know because it keeps improving. It's like the envelope keeps expanding. So I don't know, like also like we are just like, we haven't even like tried to go to a different set of frequencies and explore that or like laser or light or something like this. So I would say we really don't know because we are talking about like signals that is around us that capture so much information, and how much information it captures about us and how much is extractable of that. I mean, it's something to like keep pushing the envelope. Sure. The mic, I guess, was
All right,
Prabal.
I think we've got the last question here.
You briefly mentioned that these waves can even pick up the pulsations of the arteries. So have you picked up on any heart rates or arrhythmias or things like that, or blood pressure?
So we have like, we show that we can get like heart rate of the different individuals, and but we didn't take the heart rate as far. Like we don't deploy it in the patient's homes like now, because it's easier to get like pulsing with wearables. So we try to fit the fill in the gap, basically, like focus more on neurological and respiratory signal. But we can get heartbeats, yeah. We can even get the RR interval, like the every single beat. And some of the data that happens there has the opening of different valves, and when you look at the pattern, because it's not the electric signal, it's more like the motion-related signal.
All right, so with that, let's give Dina one more round of applause.
Thank you, Gary. Thanks, Papa.